On number 24, we are to graph 3 periods of the function. So that's where you have to have a great attention to detail on setting your scale so that you have room to create 3 periods of the function. So the first thing we need to do is to jot down that our amplitude, which is our A, is, and you can make that capital A or lowercase a, it's different in different textbooks, but remember it's the absolute value of the coefficient, and in this case that's positive 3. So it's good either way. Alright, then the period, remember for sine and cosine, is 2 pi divided by b, and b is the coefficient on the inside, on x. So that would be equal to 2 pi times 2, because we reciprocate the 2 when we change it to multiplication, so our period is 4 pi. So that means for one cycle of the graph, we need 4 pi. So that means we're going to have to kind of squeeze our scale horizontally to get that in. So we are going to set our first mark here, which is 4 boxes, at 2 pi. So before we start graphing the one we were assigned to graph, let's go ahead and graph the parent as a comparison. And remember that cosine at 0 is 1, so we're going to plot a point there. And then the cosine is 0 again at 2 pi, so we're going to plot a point there as well. Halfway between there is when cosine is negative 1, so we're going to go ahead and plot that point. And then halfway between our peaks and valleys we have a 0, and that's the structure of the sinusoidal curve, so it makes it easier to think about how to graph it if you understand that. That was a little too curved on that side with a scale. Alright, close enough. So there's the parent. Well, now we're going to get our graph that we were assigned on here with it, and we're going to go with this dark purple color for the contrast, and here we go. So now we have a period of 4 pi. That means that where the period of this yellow graph was 2 pi, we know that our purple graph is going to be double the width with the same shape. Okay? But not only is it going to be stretched to 4 pi, it's going to have an amplitude of 3, so wherever this one hits 1 and negative 1, our new graph is going to hit 3 or negative 3. And since the 3 was positive, it's not turned upside down, it's oriented just like this graph. But now we're going to hit at 3 on the y-axis, and then all the way out at 4 pi we're going to go up to 3, and then halfway in between we're going to go down to negative 3. And then halfway between those 2 points we have a valley, a dip point of negative 3, and then halfway between our negative 3 and positive 3 on each side we're going to have a 0. So those are our points that we can cut. Let me see if I can do a better job. We're going to trace those points. Come from this side, see if I can do better. These take practice, and even after you've practiced, depending on what medium you're using, they can be really tedious. So bear with me while I get this right. Okay, not bad for one period. So now we're going to use this pattern of these points that we've plotted to get our other 2 periods. So I'm going to do one to the right and one to the left. Well, you'll notice that the orientation between the 0 and the peak is 2 boxes over, so we're going to go 2 boxes to the right and make a 0. And when I say 2 boxes to the right, I mean 2 boxes to the right of the peak x value or theta value. So that would be here. For some reason my pen is not wanting to cooperate. There we go. It's a big ugly point, but it's there. Alright, so I know the graph is going to come down and hit there. And then from there I'm going to go to the right 2 and down 6 to follow the pattern to get to that dip. And then I'm going to go to the right 2 and up back to the x-axis and get that piece, and then go to the right 2 and up to 3, and there's now 2 periods. Well, we need one more. Let's slide back over here to the left and do one more period. So again, I'm going to go to the left 2 and back down to the x-axis, and then I'm going to go to the left 2 more and down 3. There we go. And then to the left 2 and back up to the x-axis. And then to the left 2 more and back up to our final peak, which will be the last point we plot for this graph. And then we're going to draw it out. Not perfect, but done. There's 3 cycles or 3 periods of this graph. And I believe that's all we had to do. On to number 30. Here we were to specify the period and amplitude of y equals 2 cosine 3x and then give the viewing window shown. Alright, well, the amplitude is easy. It's positive 2, so we don't even have to think. So A is 2. And our period is 2 pi over b, and our b is positive also, so we can just stick a 3 on it. And there's nothing to do to clean that up, so our period is 2 pi thirds. So to describe our viewing window, we need to think about what the implications of what we just said. If we have an amplitude of 2, where our cosine graph would normally peak at 1, it should peak at 2. So that tells us that our scale is 1, and our window vertically, so we'll do the second part first because that's the easy part. So our y coordinates go from -4 to +4 because it goes 2 steps past our 2 in each direction. And then the period being 2 pi thirds means that wherever I see 1 full cycle, that's 2 pi thirds. Well, this is a cosine graph, peaks at the y-axis, dips halfway in between and peaks again, so from here to here is 1 period. So this has to be 2 pi thirds on this side, and it does the same thing on the left. So this is -2 pi thirds. So what seemed like a scary problem is actually pretty straightforward here. So that gives us our x interval for our window. So that's -2 pi thirds, comma, +2 pi thirds. And we're done with that problem. Number 50. This one's a little tricky. It's kind of a little higher level question than what we've had before on having to explain the transformations of the parent. Well, this is not a parent. It's transformations of one graph into another. It says to describe the transformations required to obtain the graph of y sub 2 equals cosine x plus pi fourths from the graph of y sub 1 equals 2 cosine x plus pi thirds. So we're starting, it's like instead of having a parent graph here, we have the graph of 2 cosine x plus pi thirds. So basically, to go from y1 to y2, we have to omit the effects of having the a equals 2. Okay, so what would that do graphically? Well, the amplitude of our y sub 1 graph would have peaks at 2 and -2, and the amplitude of our y sub 2 graph has peaks of 1 and -1. So basically we're going to shrink 1 to get the other, to get 2. So we would say we need a vertical shrink by 1/2. So basically we're cutting our peaks and dips in half. Okay? And remember, amplitude is just a measure of how far from the center line you are, the center horizontal. Okay? Well, now we have to adjust for the fact that our slide to the left on the y sub 1 graph of pi thirds now needs a slide to the left of pi fourths, so we need to figure out that difference. Well, it's really simple analytically to think about. So in essence, I want to get rid of pi thirds. So I'm going to sort of, it's like I'm taking it away. So I'm going to say the negative pi thirds to get rid of what I have, and now I want to add back pi fourths to go in that direction. Well, then you just add your fractions. And you may or may not have ever seen the little butterfly technique, but you multiply the bottom of one fraction by the top of the other, which would give us, in this case, -4 pi. and then the bottom of the first fraction times the top of the other, and that would give us 3 pi, and multiply the denominators. Well, if you do that here, you get negative 4 pi, and I don't really have room to write there, so let me try something, squeeze this down just a little bit. So negative 4 pi, and then plus, because you take the sign of the middle, and then you take the top of the right, all over 12. Well, negative 4 pi plus 3 pi is negative pi over 12. Well, that's the number we're looking for. It's the magic number. So now we're ready to answer the question. And that is, we need a horizontal shift to the right pi 12ths. And we are finished with number 50. Then we have one last graph and then one more question, which is actually pretty quick and simple, and we'll be done with this video. Number 53 says to select the pair of functions that have identical graphs. Well, my suggestion here would be just to graph them for practice. So let's graph y equals cosine x, and we'll just do one period and see how it looks. Alright, remember cosine is 1 at 0, is 0 at negative pi halves, because remember negative pi halves would be going clockwise, so it would be at the point on the unit circle would be 0, negative 1. So then it is 0 again on the right side at the reflected value pi halves, and then is negative 1 at pi. I think I'm still going by 2s. Or no, I'm not going by 2s on this one, am I? I'm going by 4s. So we're going to go here for my negative 1. And then need to come back up one more time to 3 pi halves to where it would be 0 again. So that should take care of me. Let me pull out a little bit and see that. Alright, so now we trace that. And you could just plot the points, but if all you're doing is plotting points, you're going to go cross-eyed trying to figure out which one went with which thing you sketched. Alright, so this is graph A. Alright, well now I'm going to switch colors and graph B, which is the sine, but it's the sine graph moved to the left pi halves. Well, the sine graph normally goes through the origin, so I'm going to just put a little slash there to remind you that it normally goes through the origin, but we're going to slide that point to the left pi halves, and look where that puts us, right back where we started the other one. And then after it goes through the origin, it peaks at pi halves at 1, which would be here. But again, if I move that one to the left pi halves to make up for that horizontal translation, I end up back on top of my graph. We'll do one more to prove that these are the same graph, and that is after it's 1 at pi halves, it would be 0 at pi, which is here, but again slid to the left. So we see that that is in fact the same graph. So these two have identical graphs, but just for practice of all this graphing stuff, let's look at the last one. Well, first of all, we know that can't be this, the same thing as cosine, because our function transformation knowledge tells us that this would be the cosine graph slid pi halves to the left, and that would take our point at the y-axis and move it over here. So clearly that one would not work. And then we have one more example to close out this video, and this will be the last example for 4. This one's actually a pretty simple problem, and it might seem scary when you first read it, but we are to construct a sinusoid with amplitude 3.2 and period pi sevenths that goes through the point 50. Okay, here's the deal. Both sine and cosine are sinusoidal graphs because they can both be expressed as sine graphs if you transform them. So my suggestion would be to always start with sine, just because sine goes through the origin and it's just easier to think about. So with an amplitude 3.2, we know that it's going to start out as 3.2 times the sine of something, Well, then when we see that we have a period of pi sevenths, we need to step back and do a little scratch work here to figure out what the implications are. Well, remember the period of any sinusoidal sine or cosine is 2 pi over b. Well, they just told us that our period here equals pi sevenths. So you set those two equal, and then we could divide off a pi off of each side. So basically we have 1 over 7 equals 2 over b. We cross multiply, and we discover that b is 14. Well, that makes it really simple. So we go in here and put in parentheses our x, and then pause, because now we want to address the fact that this graph goes through the point 5, 0. Well, if the sine graph goes through 0, 0, and this graph goes through 5, 0, we know that our sine graph needs to move to the right 5, so we're going to go inside this parenthesis that's inside the sine's parentheses and put a minus 5, and we can stop there. And the only other thing we could do to our function we just constructed, if I can talk, we could distribute the 14 on the inside. So you might also see the same function as y equals 3.2 sine of 14x minus 90. And that's that. And the last of the video.